Okay, so it looked like there were, so remind me again, so this is review session 2. And so we're going to do, there was a request for talking about phase encode for spin warp. And then also there was a question about problem, which problem was that? 3C, okay, bring that up. So homework problem 3C, okay. Is there any other topics that people want covered? Yes.
The problem is problem for the second one.
That's on the homework?
Yeah.
Okay. Problem for point 2? Okay. All right, so that's good. So was anyone who wasn't at the review session on Monday who wants more coverage, or is this is what we'll cover unless people ask. So this is really meant for you to ask questions. So we'll go over these 3 things, and then if this triggers questions or there's a topic you'd like to have covered, we'll talk about it here. And then in the lecture, we'll go over some of the remaining quiz problems as we cover the material. Okay. All right, anything else before we get started? All right, why don't we start with problem 3C. And that is, you are asked to figure out a simpler way of taking advantage of the geometry of the object to reduce the total scan time. Okay, so your object was something like this, right? And so you had some FOV that was big enough to capture these objects, right? So you had some FOV in the x direction and some FOV in the y direction. And the question was, you know, it's going to take time for you to do all these phase. So in the kx direction, sorry, this is ky. You know, to cover this FOV, you've got to do all these phase encode lines, right? And that takes time. So the question is there a way where you could do less phase encode lines? Could you look at this problem slightly differently and do less phase encode lines? So did anyone come up with any ideas on that? Yes?
Either rotate the object or mathematically rotate your axes so that the object kind of lies on the x-axis.
Yeah, so did everyone hear that? So you could either rotate the object physically or just rotate your coordinate system, which you can do in the software, and just make it so that the FOV in the y direction is less. All right, so the idea would be you could just think of this as your FOV now. Okay, and so the key is always, for spin warp, the FOV in the y direction takes the most time, and so if you can figure out a way to shorten that, that's a good trade-off. A similar issue comes up in terms of if you're looking at a human being, right, and you're trying to image their spine, okay, and you have a choice of, so the FOV, let's say, is going to be this, right? That's your FOV. Okay. So what do you want? This FOV should be which FOV, X or Y? So you can either choose X or Y for either of them. So it's up to you to decide which is phase encode and which is read. And so by definition, X is always the readout, and Y is always the phase encode. So given the fact that you know that the phase encode in spin warp is the thing that takes the most time, which one of these directions should it be? Should it be this vertical direction that's the FOV in the Y, or should it be this direction across? Across, right, because it's shorter, right? So you'd want to make this direction FOV Y and this direction FOV of X. Okay? And then what we talked about in lecture was the fact that, you know, you think, oh, well, if I make my FOV of Y, X like that, then aren't I going to get aliasing of the head? You know, isn't the head going to alias down into the spine? And that's where we said, yes, it would, but you can apply this filter in the time domain that just filters out those spins. So it's a sort of neat trick that lets you get away with putting the FOV in the x direction along the long direction, and then also making sure that you don't have to make the FOV super large to avoid aliasing. All right. So are there any questions on? Yes, question.
So you're not supposed to calculate the minimum scan time for that recording system?
Yeah, you are. You are.
Right.
Yeah. So you basically, but the calculation is simply that.
Because for me, that turned out to be, it was reduced by more than a factor of 2.
Yeah, that's fine. Doing better than factor 2. Doing better than you're asked for is always good in engineering.
Okay, so
Yeah. Like if your boss asks you for a 10% improvement and you deliver 30%, he's going to be like, great. Yeah, so that's fine. So the factor of 2 is somewhat misleading, right? I mean, it's sort of like you can actually do better than a factor of 2. And each year I change the problem a little bit, so the factor of 2 doesn't always. Some years it's closer, some years it's farther away. Okay, are there any other questions on that problem? All right, so we've knocked off problem 3C, right? So let's look at problem 4.2 on the homework. So which one is that? Okay, so this is a good one because it's talking about the spin warp pulse sequence. So we've got a spin warp pulse sequence. And the user increases the FOV by a factor of 2. Okay, in the readout direction. So FOV of x goes up by a factor of 2. And then it's asking you which of the following must happen. So then we're assuming the time for each readout sample, delta t, is constant, right? And tau, the width of the readout gradient, is constant. So what that means in terms of our readout is that this is our spin warp pulse sequence. This tau is kept constant, and this delta t is kept constant, right? Okay, so with all these problems, you want to sort of look at the chain of events that occurs. Let's see. And everything else constant too, right? So basically everything else constant. Now, that's probably worded not perfectly, not as well as it could be, because some things are going to change, right? So it's not like everything is constant. So when I say the parameter held constant, typically I mean FOV and resolution. Okay, so all other FOV and resolution. So in this case, it'd be FOV in the y and delta x, delta y would be held constant. Okay, so that's what all other would indicate. All right, so let's take a look at, so with all these problems, you're always trying to look at the chain of events. So if the FOV in the x direction increases by a factor of 2, what's the immediate impact on a k-space parameter? What has to go down? Delta kx, right? Okay, and we know delta kx, if this is gxr, it's just gamma over 2 pi gxr times delta t. Okay, so this went down by a factor of 2. This is constant. So this must go down by a factor of 2. Okay, so then that's choice D, right? Everyone got that? Okay, so that's one choice. And then in this case, it said there might be more than one option. So let's look at that. So the FOV has changed, and the delta x is the same, right? So FOV of x has gone up by a factor of 2, but delta x is the same. Okay, what does that say about how many voxels we're going to have in the x direction? Is it going to go up or down? So I've got this FOV, and I've increased it by a factor of 2, right? But my resolution is the same. So do I have more or less voxels? I've got more. So the number of voxels is probably going to go by a factor of 2, just in the image domain. You can also look at the k-space domain. WKX is equal to 1 over delta x, right? So that stays the same. But delta kx has gone down by a factor of 2. So this width in k-space has stayed the same, but the spacing has gone down by a factor of 2. So once again, you have double the number of samples. Okay? So in either case, whether you think about it in the image domain or the k-space domain, you're doubling the number of samples you need to get across to get the data you want. And therefore, we would say that, so it doesn't say anything about the number of samples, but it does say something about the temporal width of the readout gradient. Okay? So if the number of samples doubles, what happens to this temporal width? So the temporal width would be this, we'll call it tau sub x. It's got to double, right? So then therefore tau sub x must go up by a factor of 2. So that's E, right? So we've covered C, D, E, and F because those were forced choices. Do either A or B apply? No, because we're not doing anything on the phasing codirection. Okay, so everyone got that? Okay. So for those of you who came in later, what we're doing is we just went over homework problem 3C. We just did problem 4.2. And now we're going to talk a little bit about phase encode for spin warp. Like what if you were given a problem where the phase encode changed? And so I'm just going to make up a problem on the fly. Okay. That said, as we've been going through this material, are there any other questions that have come up that people want covered? Yes. Yeah, so what I'm going to do is I'm going to actually go over those problems. I thought about that, and then as I was making up the lecture last night, I realized you don't have the material to go over that. So during the lecture today, I'll go over the quiz problems. Yeah, so wait for another hour. Okay. Any other things that people want covered? Okay, so we'll just do this, and then if you think of anything, let me know, and otherwise, it'll be a sort of free session. Okay, so let's come up with a phase encode problem on the fly. Okay, so let's assume that we're doing spin warp. Okay, and now let's say the FOV was originally 256 in the y direction and in the x direction, and delta x equals delta y equals, say, 1 millimeter. Okay, and now there's a number of things we could do, but let's just say one of the things is a simple question is what happens if the FOV in the y direction goes down by a factor of 2, but keep this tau sub y constant. Okay, so we're just going to go through what things must change for that to happen. All right, so as before, if the FOV in the y direction goes down by a factor of 2, then the first thing you write down is, well, then obviously delta ky goes up by a factor of 2. Okay, and so what that means is if we're looking at these phase encodes, so this is kept constant, this tau y is kept constant. And so the only other parameter we have to play with is this incremental gradient that we increase by each phase encode. So because that delta ky is equal to gamma over 2 pi gyi tau sub y, we said that this one up by a factor of 2, this is constant, and therefore this one must also go by a factor of 2. Okay, so if that was one of the we're making up a problem on the fly for those of you who just came in. So if that was one of the options, then you would say that incremental gradient should increase by a factor of 2. All right. And the only other thing is then what's this G, let's call this Gy max. Like how far out do you go out in k space, right? So let's think about that. That's the GY max is directly related to what parameter in K-space? What does it control? So if I have a gradient with GY max and I play that gradient out, that takes me out to the farthest place in K-space, right? Which is just KY max, right? So it directly controls that, and that's just equal to half of the width in K-space, right? And that's equal to 1 over delta y over 2, right? Okay. So this stays the same, right? This stays the same, right? This delta y stays the same because you're given that in the problem. Therefore, this stays the same, and this stays the same, and therefore this doesn't change. Okay. So if one of the options was change the maximum gradient, then that would not be the right option. Okay. So we've covered the GYI, we've covered the GY max. What's the remaining thing we need to figure out? There's one more parameter we need to figure out for the phase encode. Go ahead. Yeah, or n phase. Yeah, so how many phase encodes do we do? So is that going to change or not? So we know that the delta ky went up by a factor of 2, right? But the wky is the same. So the amount of K-space we're covering in the y direction is the same, but the step size has gone up by a factor of 2. So what's going to happen to the number of phase encodes? It's got to go down by a factor of 2, right? So that just means that n ky goes down by a factor of 2. All right? And you could have gone also the fact that, the same thing, FOV of y went down by a factor of 2, but delta y is the same. And so in image space, you've reduced your field of view by 2, but you kept your resolution the same. So the number of samples you need in y is also reduced. So n sub y would also be down by a factor of 2. And for these very simple spin warp questions, the number of samples you have in physical space, if I have 100 different numbers in voxels in physical space, by just conservation of sort of information, I probably need 100 different numbers in K-space. Okay. Now that's for these very simple problems. Later on, you can get away with reducing it, but for now, for these problems, it's fine to use that as a sanity check. All right, any other questions? So that was just a made-up question, but it covers sort of all the different relations that you would just need to know. Okay. So basically, all these problems come down to is how much are you covering and what's your step size? And then the gradients that you need to do that. Okay. So it's really just talking about, it's sort of the nuts and bolts of MR in terms of covering K-space. Okay, are there any other questions either on that people want to go over in terms of that we didn't go over on Monday, or that you had questions about still that weren't resolved for Monday or on the homework? Yes, way in the back. In the homework? Okay. Yeah, so let's look at that. I'm not going to do the whole homework for you, but let's I mean, we do have time to do all the homework, but that would sort of defeat the purpose. But let's just go through enough of it so you can figure out how to go through this problem. Okay. So you're told you've got this inversion recovery sequence, which means you went down to minus m sub 0, and then you acquired at this point to null out fat. Okay, so that's the fat T1 recovery, right? And then probably the, let's see, fat has the shortest T1, right? So if I had muscle that was inverted, it would have gone something like this, right? Everyone okay with that? Okay. So basically, muscle would still be negative. in terms of its magnetization. But that's okay because if I have something negative and I apply a 90-degree pulse to it, it does flip it onto the transverse plane. Okay, so that's still okay. And then the fat is 0. So the question says, well, what happens if instead of starting off there, you started off here, right? So where do you think, will fat still be zeroed out? Okay, will it be positive or negative? It'll be up here, right? It's going to go like that, right? And then what about muscle? It depends, right? It depends on the T1 values you plug in. So what are the choices you're given? So it's either D or it's F, right? Okay. Everything else is the same. Expected volume. Imaging. So yeah, I think for that one, right, you're probably not given enough information, but magnetization of the fat will be positive, negative. Okay, so you're trying to decide between D and F. Okay. Yeah, that's a good question. Okay, go ahead. Someone else has an answer.
Doesn't it also mention that at the point magnetization before anything happens at the very beginning, so it would be at negative and 0.
Yeah, so what that means is, okay, so let me answer that question first. So here's minus m naught over 2. So that's when we apply the inversion pulse. What that means, and then we wait some amount of time, inversion time. So we wait some inversion time. And at that inversion time is where we apply our 90-degree excitation pulse. So it is still asking what is the value of the things there. Yeah, that's a good question. Let me look up the answer that I came up with several years ago, and we'll see if I still agree with myself. So yeah, just hold on for that. Yes, question.
So for now, if you actually, if you do the math,
Yeah.
it turns out that it's negative.
It does turn out to be negative?
Yeah.
Okay.
Use the values of T1 that are in one of the slides.
Good. Okay. Okay. So there you go. So I'll check. I think that's. Yeah, I would if I was just sort of guessing, I would assume it's probably still negative. But yeah, if you plug in the values, it's good to know that that works. Okay. Any other questions? Yes.
I had a question with problem 3 and problem 5 actually.
Problem 3?
In 3, I wasn't sure how would you calculate the number of boxes.
Are you talking about problem 3b?
Mm-hmm.
Yes. Okay. So let's see if we can take a look at 3b. Okay, so so I'm going to ask you some questions. Okay. So let's see. What is the FOV that you need in the x direction? What FOV did you get? 9. Okay. And what about in the y direction? Okay. And then what's the resolution in each direction?
1/4.
Okay, so it's 1/4 here. Okay, so what's the how many voxels do you have in the x direction?
There's no data given, so I wasn't sure.
Oh yeah, but you know, so you have 9. You're trying to space a span of 9, and you're going. What's your step size?
We just consider step size to be
Yeah, it's like on your when you buy when you go buy your 50-inch TV, it's like 2,000 by 3,000 voxels, right? So and then what does that mean? It's like 50 inches divided by the resolution is how many voxels there are. So how many voxels do I have in the x direction?
So it would be 9 divided by 1/4.
Yeah.
Okay, I wasn't sure if I was doing that correctly.
Yeah.
Doesn't that work out the same as the number of readouts as well?
Yeah.
So it's supposed to be matched with the.
Yeah, it has to be, right? Because think about it this way: if the number of voxels is FOV over delta K, right? Oh, sorry, let me erase that. Over the resolution, right? And then the number of K-space samples, at least the way we're doing it, is WK over delta k, right? But wk just equals 1 over delta, and delta kx just equals 1 over f of e, so that just gives you the same thing, right? So these two things are, for these very simple examples, they're equivalent. So that's why you can do the sanity check. Now, as I mentioned before, people are always trying to go faster, and so there's tricks that people have come up with over the years to sort of break this speed limit. Hopefully, I think one of the projects will talk about it, and I'll ask Professor McVeigh to touch upon it as well. Okay. All right. Does that give you enough information to proceed?
But I was confused about the scan time.
Yes.
We're given TR.
Yes.
What do we consider the whole scan time?
Oh, okay, great. Okay, so that's a good question. So with spin warp, remember the way we acquire the data is line by line by line by line. Okay? And so the way that's done is we have some sequence where, let's say, we apply these 90-degree pulses, and the distance between these is TR. Okay? And after each one of these, we apply the gradients. So we apply these readout gradients that are the same each time. And then we also apply phasing cogradients that vary on each shot. All right. So each of these corresponds to one of these lines. Okay. So TR is the spacing, how much you have to wait between lines. So the total time is just how many times you have to do that times the TR. Right. So that's why there's always this. So if you can reduce the number of lines that you have to acquire, then you can reduce your scan time. Because in this problem, your TR is fixed, right? Yeah.
It would vary according to the number of phase and code variants that we have. Or
Yeah.
is the number of lines predefined already when we define the resolution?
Well, so basically, once you've decided the n sub k is what determines it, right? So whatever your n sub k is, that tells you how many lines you have to acquire. Yeah, and so that's what problem 3C is asking. So I think we did this before you came in, but the idea was, were you here when we did this one? Okay, so this was the problem, right? And the question was, how do you make the FOV? It's the FOV in the y direction that takes you the time, right? Because that determines your WKY, and you're having to have all these lines go through. So the question was, how do you make that FOVY smaller? And so the idea is you could just rotate the object or change your coordinate system. Okay? And so then we got into this discussion of, that's just a silly homework problem, but in real life, it's very applicable because oftentimes you want to image someone's spine, right? And so therefore, you have a choice. Do you make this your phase and codirection, or do you make this your phase and codirection? If you make this your phase and codirection, you've got to do a lot of lines. It's going to take a lot longer. If you make this your phase and codirection, it's much shorter, so you don't have to acquire as many lines, and so the scan can be faster. Okay? And then we said, well, I'm going to make this I want to make this field of view just to cover the spine, but what about the head and what about the legs? Won't they alias into my image, right? Because the object is bigger than this field of view, right? This is my field of view, I'm saying, but my object goes much bigger. And that's where it gets into, we touched upon a little bit in class, which is if I have, if I imagine I've got this readout gradient, like that. Okay, so this is a readout gradient. So this is, let's call this, now this is the x direction because we're defining it as our readout direction. So by definition, x is always readout, y is always phase and code. That's just the standard definition that we have. And the x is what's called a logical coordinate system. So the x can be any direction. Okay. There's also physical x and y, which is the magnets x and y. And so in MR, there's always this translation between your logical coordinates and then the physical coordinates. All right. So there's a lot of rotation matrices in MR machines. But basic idea is everything in this FOV here has some frequency of spins, right? And once I go outside the FOV, the spins here are spinning at much higher frequency or much lower frequency. Okay. So if we look at the frequency domain, the spins I want are all within this frequency band here. And I just filter out all these with a low-pass filter. So that's just done right now. It's all done digitally. Okay, so those of you who have studied digital signal processing, it's essentially just a digital filter that just filters out those signals. All right. There's some analog filtering still done, but by far most of the filtering is done digitally now. Okay. All right. Are there any other questions? Yes. Well, I'll just go to you, and then we'll come back to you. Okay. Go ahead.
For the second problem where we're finding TR, one of the parts of access finding the signal to noise ratio, or like the TR that maximizes your signal to noise ratio. And I was wondering,
Can you tell me which problem you're talking about?
sorry, 13.23 in the book, so it's like the second.
Oh, okay. Yes. And what does it ask you to do again? 13.23?
It asks you to say what the TR should be to find the maximum signal to noise ratio, I think.
Yeah. Okay.
And I was wondering what the
Yeah, so the approach for that one, at least, I think the way they worded in the book is slightly misleading. They really only need to solve one problem, which is essentially, let's say you have signal for you acquire your signal for your species at T1, and then there's a signal for the species with let's say called T1A, T1B, right? So the difference in the signals is just simply S of T1A, and this is also a function of TR, right? So so these are fixed. T1A and T1B are fixed for the problem. So you're just trying to see how this delta S varies as a function of TR and maximize it. So for this one, if you just do delta S over delta TR and find out where T equals 0, that's sufficient.
So like the thing that gives you the maximum difference between your signals.
Yeah,
The same thing that's going to give you.
exactly, because they didn't tell you anything about the noise. And so in this case, it's essentially you want to just maximize that signal difference. And I mean, they could have given you more information, but for at least when I looked at the problem solution that they gave, that should be sufficient. Okay. Was there a question over here? Did you still have a question? Yes.
I still got a question about problem 3C.
Yes.
Which was,
This one here.
So we're saying that if we change the FOV to this direction, this would essentially reduce the scan time.
Mm-hmm.
But how do we explain that mathematically?
Well, let me ask you a question. Let's say you didn't want to do any math. Like, I mean, you want to be like lazy smart, right? So let's say you were I don't want to do any math, and you have this object that's small enough that you can hold in your hand and fits in the MR machine very easily. What could you do in like 1 second to solve your problem? What I'm asking you, what could you do?
Just orient the
Yeah.
object.
Yeah. And that's what people do. I mean, like, let's say, I mean, if for example, you just want to make your life easy and you can just rotate it, that's the simplest thing to do. Yeah. Now, in general, you can't. Like, you can't take a person and, yeah. Okay, anything else? Okay, so if there's nothing else, you guys have about half an hour. Oh, there was something? Or is that? Yeah. Was that? Okay. I think you were just scratching your nose. But you had a question.
If we could do just like a side-by-side as far as like image domain and then case-based domain.
Sure.
How all those different parameters, like how we use the equations actually fit in there.
Yeah, okay. That's a good question. So I'm just going to go over what I think is needed and then ask questions. So the bottom line is there's really just 4 parameters in the image domain: FOV in the x direction, FOV in the y direction, and then the resolution. Okay, so those are the things you have to specify at least 4 parameters. Out of that obviously comes 2 more parameters. So the number of x samples is just FOV of x over delta x. And the number of y samples is simply FOV of y divided by delta y. And so this is a matrix of nx by ny image. Okay, so that's all that is in the image domain. And then in the frequency domain, you have kx and ky, right? You have the width in the x and in the y direction. And then you also have your delta kx and your delta ky. Okay? And so the relationships here are I'm just going to write it for one, is like delta kx just equals 1 over FOV in the x direction, and wkx just equals 1 over delta x, and same thing for the y. All right. So then what are some of the other parameters that we talk about? Well, some of the other parameters we might talk about are the number of readout samples. So that's just equal to wkx over delta kx. Okay. And then for this, assuming that all these relationships hold, that's just equal to FOV of x over delta x. So that equals n sub x. All right, so those things match up. And same thing for number of phase encode is wky over delta ky. And it turns out that's just FOV of y over delta y. So that equals number in the y direction. Okay. So that's sort of nice. For these problems, there's always, you can sort of check your answer, because if you have a different number of samples in k-space versus image space for these problems, that's saying that you made a problem, you made an error. The other parameters we use are, especially when we're talking about gradients, is instead of talking about wkx and wky, we might think about kx max, which is the maximum gradient. And that's just, for our problems, wkx over 2, and ky max equals wky over 2. Okay. So let's see, we'll click there. And so that's in terms of, and then so that's just all those parameters being related to each other. So do you want me to talk? Do you want me to go over how it's related to the gradients now? Would that be useful, or is this enough? Okay. So let's talk about how this is useful related to the gradients. So let's look at the readout gradient. Okay, so in terms of the readout gradient, probably the easiest one to remember is just delta kx is just this area, right? That's covered with a gamma 2 pi scaling factor. So it's just gamma over 2 pi times gxr times delta t. Okay. But it's essentially how much area you acquire each delta t for a spin-warp pulse sequence. The other parameter you can come up with is, what's this total time, tau sub x? Okay, and there's a couple ways you can do that. The easiest way is say tau sub x is equal to n read times delta t, right? Which just equals w kx over delta kx times delta t, okay? Which just equals nx times delta t. So that's one way you could come up with it. The other way you could come up with it is saying this total gradient area here, that total gradient area is equal to gamma over 2 pi times gxr times tau sub x. Okay? And that has to be equal to 1 over delta x, because it's equal to wkx. Okay. So then solving for this, we could say that, for example, tau sub x equals wkx over gamma over 2 pi gxr. Okay. And that is just equal to wkx. So from here, we know that gamma over 2 pi gxr is just delta kx over delta t. Okay? So this is going to be delta x over delta t, so the delta t goes here, and that's exactly the same thing we got there. So I wouldn't recommend memorizing all these things. I mean, but just sort of the concepts of basically there's always a width you're trying to cover, how you're how finely you're covering it, and then the gradients that allow you to cover that. All right. There's one other parameter we haven't really talked about in this class, which is, what about this guy here? How do you design this guy? Okay. And so this is typically where, if you're given a problem on this, you want to, in general, make this time as short as possible. Okay, so this is where the problems come in, where you're asked to go out someplace in k-space and do it as quickly as possible, assuming some maximum gradient. So for example, let's do an example of that. Let's say your Gmax is 5 Gauss per centimeter. Okay, so what's the G not G? What is tau sub 1? Okay, so how would you do that? Well, this gradient here, has to get you out to minus kx max, right? It has to get you halfway out. It's to the most negative part of k-space, so you can start your line, right? So this gradient area, gamma over 2 pi times Gmax times tau sub 1 has to get you to kx max. Right, that's its job, is to drive you out there. That's just equal to wkx over 2, which is just 1 over delta x over 2. Okay? And so therefore, you're given the resolution, you're given the Gmax, so you can solve for the tau sub 1. All right, so that's all you really need to do for the readout. That is literally all the calculations you would ever do, assuming rectangular gradients. Now in the real world, you can't just turn gradients on and off. And so in the real world, you have to have these trapezoidal gradients, or you have some sort of gradients. And then it becomes slightly more complicated because you have to take into account these sorts of areas. So I used to have problems like this, but it was just too much algebra, so now we just keep it simple. But if you go into MR, then you have to do that. All right. So is everyone okay with the readout gradient? Okay, so yeah, it's a question.
On that, I had a question, but that's when you're in problem 5.
Yeah?
So where you were supposed to calculate the sequence parameters, which is G1, G2, G3.
Yes.
I was just confused there because so we're given the values of the time period of the gradients. But
Yes.
I was wondering when we're actually calculating, what do we consider tau as? Delta t is also something that's unknown.
You mean specifically for this problem, problem 5? You mean the tau that's in the figure? So that tau is just 10 microseconds. So you can assume it's 10 microseconds. Yeah. So in general, if you're given on a problem any parameters with numbers, that's unless you're told otherwise, just assume that that's the value you should use.
And is to be considered the same for G1 also, we're given 6 working microseconds?
Oh, I see. So the G1 is, right, you have to figure out delta t, right? But how would you figure out delta t?
Since we don't have G1.
Well, you don't need G1 to figure out delta t. So you're given the FOV in the x direction is 256, and the resolution is 4. So how many samples are there in the x direction? 64. Okay. And so how many readout samples would you need in the kx direction? Okay. So what's delta t?
Oh.
Yeah.
Okay.
Yeah. Yeah. Yeah.
I was considering 64 samples over the entire length of the repeating gradient. I didn't realize it would just be for a single pulse.
Yes, that's the readout. So each of those is a readout gradient that goes all the way across kx. Okay. So we have about 10 more minutes for this review session. So let's go through the phasing code. Okay. So this one is like this, right? And so from a design problem, there's a number of ways we can do it. But let's, for the purpose of being a little more realistic, let's assume that we always want to take maximum advantage of our system parameters. So we're going to want to max it out and go to Gmax and minus Gmax, right? We don't want to leave anything on the table. We want to use the full gradients that we have. So for example, this case, you might be given that Gmax is equal to 5. Let's say you're given that it equals 5 Gauss per centimeter. Okay. So then this is going to leave this as a free parameter. Tau sub y is up to you to figure out. And it's exactly the same calculation we did for tau sub 1, right? That you could say gamma over 2 pi Gmax times tau sub y is going to be now my ky max. Okay, and that's just equal to wky over 2 equals 1 over delta y over 2. All right, and once again, if you're given the resolution in y, you're given Gmax, you solve for tau sub y. All right, and so this is what you would solve for. And then the only other thing you would have to design for the readout gradient is this incremental gradient, GYI. Okay? And so the easiest way to solve that, there's a couple ways of doing it. Let's do both of them. Is that delta ky is equal to gamma over 2 pi GYI times tau sub y, which you solve for here, right? So you can take your value for tau sub y, put it in there, and this just equals 1 over the FOV in the y direction. All right? And so you can solve, you know tau sub y, you know FOV of y, you can solve for GYI. Everyone okay with that? Okay. And so that's basically, in that sense, it's actually fairly straightforward, the design. Okay. Yes, question. GYP might have been, I think, correct me if I'm wrong, it's probably this one, right? The maximum gradient? Yeah. But in this case, we're saying we want it to just be the maximum gradient. So we're just setting it to the limit. Yeah. Because we want to maximize that tau sub y. Okay.
The only time you have like a different value for GYP is if you were using a value less than that.
Yes, exactly. Exactly. Yeah. Okay. Any other questions? Okay. So I'll stop the recording now, but if you obviously have questions, you can just come up and ask me in person for the next few minutes, and then we'll take a break and then start at 11.